Welcome. In this, we look at the relevance of graded ideals in geometry. It is through a construction called Proj of a graded ring. And so we will only discuss the very basics, just enough to motivate why these computations with graded ideals are useful. If you want to look at more, understand more about these constructions, then you should read a book on scheme theory, or for example, Hartshorne chapter 2, or any book of that sort of, which covers that sort of material. Okay, so for us, K would be a field. So this definition is restricted to the case where K is a field. The general definition is a little bit different, but we'll just keep it simple for ourselves. Okay, so S is a polynomial ring in n plus 1 variables, x0 through xn, and degree of xi is 1 for all I, and M is a homogeneous maximal ideal. Okay, so this is the unique homogeneous maximal ideal. Okay, and we define Proj of S to be this set, okay, and we will give it a topology in a minute. So these are homogeneous prime ideals strictly contained inside the homogeneous maximal ideal. In the general case, this would just say M is not inside P. Okay, but this is the for us it's equivalent to this, so we'll just keep this as our definition. Okay. So now how we give it the Zariski topology. So closed sets. So here some abusive notation. I don't want to introduce some new notation just for this one. So here when we mean V of I, where I is a homogeneous ideal of S, then we look at the elements P in Proj S, meaning homogeneous prime ideals not equal to the maximal ideal. Okay, so that contain I. Okay, so all the ideals in this page here are homogeneous, and this is P is a prime ideal, not equal to the homogeneous maximal ideal. Okay. So this is Zariski topology. So for a homogeneous non-zero element F, we can define UF to be the homogeneous prime ideals which don't contain F. Okay. So this is the complement of V of F, V of the ideal generated by F. So these are open. Okay. And these will be the basic open subsets in this topology. So suppose that I is generated by some F1 through Fm, okay, homogeneous. Okay. Then if P contains I, if and only if for all I, P does not contain P contains Fi. Okay. This is the condition that P is inside V of I, homogeneous prime. So the P is also homogeneous in this equation, and this is the condition that P is not inside UFI. Okay. So it says that P is in Vi if and only if P is not in UFI for all I. So then this would say that V of I is Proj of S minus the union of UFI. This Proj S minus this, maybe 1 to M. Okay, so that's the so every closed set, or in other words, the open set Proj S minus Vi is a union of these things. Okay, so this is okay. We also need to check that the UFI, so the UFI are meant to be basic open sets in that topology. We need to check one more thing, which is that UF intersect UG contains some open set of the same kind, the basic open set. So let's ask this. So P is in UF intersect UG if and only if F is not in P and G is not in P. If and only if the product is not in P, this is where its prime is used. It's used in these definitions also, but because it is prime. But this is the same thing as UFG. Okay. So therefore, this intersection of two basic open sets is itself as a basic open set. So then it satisfies the requirements to be a basic collection of basic open sets. Okay, so this is Zariski topology on Proj. Okay, and so there is a relation between spec of a polynomial ring in n variables and Proj of a polynomial ring in n+1 variables, and this is what it is, and we will explore this in the next few lectures. We will try to understand this carefully in the next few lectures, not in the immediate one, but some lecture later. Okay, so let P be in Proj. Okay, so it's a homogeneous prime not equal to the maximal ideal. Then let xi be not in P. If every xi is in P, then P has to be M, the homogeneous maximal ideal. So there is some I with this property. Okay. So now take S, localize at xi. This is just localizing. Okay. Now this is a graded ring. Okay. And take its degree P, 0 P's. So what is? Let's just write down. This is the localization. Just inverting xi, it is a graded ring. Okay, and this whole thing is called the is just taking the degree 0 piece of that graded ring. Okay, so this is the degree 0 piece of the graded ring. Sxi. Okay. So now take this one. Okay. So this is isomorphic to. Okay. So that's the relation. This is isomorphic to K adjoint some new n variables. Call them y0 up to yi minus 1. Then skip yi. Take yi plus 1 and then yn. Okay. And what are these yi's? Where yi okay, is the ratio, yj is the ratio xj over xi. Okay. So this one can check. So this is what this is. And so we have now two topological spaces. We have uxi, which was, so we had uxi, which was all the homogeneous prime ideals not containing, okay, so this is P such that P in spec Proj not containing xi. Okay, and on this side we have some polynomial ring. So I'll just write for simplicity yi with a hat to denote that that has been omitted, and then yn. So there is only, although the list has only n plus 1, ith has been omitted. So it's just this. Okay. So there is a spec of this ring. Okay. So there is a homeomorphism between these two. So these things I have not proved because proving them will take sort of outside, I mean, it will take a little while. So you can look at a book in scheme theory to understand this. This is mostly to motivate why, I mean, this part is mostly to motivate how to switch from the non-graded case to the graded case. We will see later. And then also that there are certain advantages working in the graded case. Okay. So this is what it is. And what is the map? Okay. One could look, so this is the map. One takes P here, so in that one direction one can give the map. One takes P here, and then P goes to, well, first we inverted xi. Okay, so this is a prime ideal in Sxi, and then contracted it to the smaller subring Sxi in degree 0, and that would give this map. Okay. So a prime ideal corresponds to invert xi and then just look at its degree 0 piece. Okay, so so this gives this is a homeomorphism. Okay, so we'll use that fact perhaps without without any further explanation. Okay. So notation Proj of a polynomial ring in n+1 variables will be denoted as Pnk, and this will just be, we'll just call it Pn. We are not going to work with multiple vector space, multiple fields. We'll just call it Pn. Okay. Okay. So one can just to get some geometric intuition behind this thing. Okay. Now assume the case algebraically closed. Okay. Then every maximal ideal. Yeah. So remember, the identification between these two rings is that yi here is the ratio xi minus xj over xi. Okay. So every maximal ideal of this ring, that open subset, ring corresponding to that open subset, y0 skip yi and yn, this ring is of the form y0 minus a0 up to some yn minus an. There is no ith term, there's just n terms inside this. Okay. Now we can work backwards through this and see what P is. So this corresponds to the homogeneous prime ideal. Okay. x0 minus a0 xi. Remember, it was xi. So here we were saying y0 is a0. So which means that x0 over xi is a0. So that back in S would be this relation. And then x1 minus a1 xi and so on. There will be no relation indexed by I inside here. Okay. And then finally xn minus an xn. Okay. There is no an, ai. So this still has only n terms in it, not n plus 1. Okay. And so this is a prime ideal that one can check. Okay. So if this is okay, so this is a thing. So this is a maximal. This is maximal. Okay, among the elements of Proj. I mean, this is not a maximal ideal in S. But if you consider homogeneous prime ideals which are not equal to the homogeneous maximal ideal, this is in that collection this is maximal. Okay. So in other words, this gives a closed point of Proj. I mean, there is in the closure of the singleton set, there is nothing else. So it's just a closed point. Okay, so this is what we mean. Okay, so let's go back to. So this is actually what would be a point inside Proj. Okay, and we know in this ring, this actually did correspond to a point. But on the other hand, okay, this prime ideal defines a line, okay, line with these slopes. So it's a line in Kn plus 1, okay, with these slopes. x0 over xi is slope is a0, and x1 over xi slope a1, and so on. So we can write it, defines a line, or defines the line through the origin and a0 through an inside Kn plus 1. That's, I mean, if, so this is a prime ideal, this is an ideal if any element of sorry, this is not correct, there is only n terms in this, and a0 up to ai minus 1, 1 ai plus 1 up to an. Okay, there are, okay, it is the line through this point, and this says those ratios, the slopes are correct. X0 is a0 times xi, and so on. Xj is aj times xi for j different from I. Okay, so it corresponds to the line through the origin and this point inside kn plus 1. Okay, that is. So let's just quickly check without actually, I won't write it. So if you have a point that satisfies these equations, okay, then, well, to actually identify the point, all that we have to give is just to specify what its value of xi, what the value of xi is. If the value of xi is non-zero, then it will be a multiple of this point. If the value of xi is 0, then this point will be the origin. That's the only solution. Okay, so this defines a line through this origin. And okay, so what we have done is, so any multiple, any non-zero scalar multiple of this is also the same point in the projective space. It corresponds to the same ideal. So what we have done really is construct a topological space with the following property. We took kn plus 1, then we took away the origin, and on that we acted by the so let's say equivalence relation. And what is the equivalence relation? A1 through A0 through AN, or maybe just to not to confuse with the previous A's, let's call these things B0 through Bn is equivalent to C0 through Cn if and only if. So this is the definition, if where that is given by. Okay, so this is if and only if there exists some lambda inside K, the units of K, the non-zero elements of K, such that the vector B, so let's call this thing B, let's call this thing B, and let's call this thing C. B is lambda times C. So it is identified at the level of points, it's identifying things like this. But you know, the space already has some prime ideals, so it's a little bit more difficult to describe it at that level, but for a picture one can keep this in our mind. Okay, so the first observation that we would like to make is, this is built from the previous lecture's proposition. Okay. Dimension of V of I, so now this is, remember this is inside Proj of S, okay, not inside Spec of S. So I homogeneous, I inside S homogeneous. Okay. This is equal to dimension of S mod I minus 1. Okay. And this is the first statement. And 2, V of I is empty if and only if I is primary to the homogeneous maximal ideal. In other words, for every variable, some power of the variable appears inside I. Okay, so this is what we have. So let's prove these things. This is not very difficult. Okay. So when we say dimension of V of I, we mean a chain of primes inside V of I. We talked about why the Kuhl dimension for ring is same thing as the topological notion of dimension by filtration by irreducibles for topological spaces, and it's the same thing here. So if so I'll just sketch this part. I mean, I will, if P0 inside PL is a chain in V of I, okay, but so this is a homogeneous prime ideal, which is not equal to the maximal ideal, then P0 inside P1 inside PL, strictly inside the homogeneous maximal ideal, is a chain in spec R mod I. Now, the dimension of the ring is determined by this value, and dimension of V of I is determined by this. Okay? So therefore, it's always at least one more, and then if you have any chain like this, then it is if this is a chain in V of I, then this is a chain in, if this is a chain in spec R mod I, then this is a chain in V of I. So in fact, we can remove this if here, and then this thing here, and then say if and only if. Okay, so this is the proof of 1, and proof of 2 is that, remember, if so 2 said that if and only if radical of I is m. If radical of I is m, then this implies that there does not. This implies that there does not exist any p homogeneous prime such that I is inside P and P is not M. Okay, that's right. That is okay, because minimal primes is just M, so this won't be. And this one implies that V of I is empty, because any such P is what would make up V of I. And if V of I empty, then this is true. And if there isn't any prime ideal containing I, and P is not equal to this, but remember I is homogeneous, so the minimal primes over I are themselves homogeneous. So that proves the other direction also. Okay, so this is the proposition. Yeah. So just a remark. We can define Proj of S mod I also. Okay. Same way, in a similar way. Homogeneous ideal as the set of Q inside S mod I, homogeneous prime ideal, such that Q is not, Q is properly contains inside maximal ideal extended to S mod I, which is the homogeneous maximal ideal of S mod I, unique homogeneous maximal ideal of S mod I. So you can take this, and then just as we did it for spec, we notice that there is a, so R, okay, so S surjects on to S mod I. This is a graded ring map, okay, preserving degree, etc. Then this one gives Proj of S mod I inside Proj of S. Okay, and image is exactly what we defined as V of I. Okay, so just a warning, it is not true that every graded map will give a map of Proj. In spec, that is the case. If you have just a map of rings, it will give a map of spec. Proj is not that straightforward. There has to be some conditions, but there will be, in this case, particular case, one can sort of explicitly verify that this surjective map induces this injection, and this is precisely what this is. Okay, so now let's look at definition. So let's try to use some of the things that we learned so far. Definition. So I inside S homogeneous. We are not as, so sorry, the assumption that K was algebraically closed was only till, where was it? Only at this point, just to get a geometric picture. Okay, so from this statement onwards, it is not relevant. It's for any field, just to clarify. Okay, I homogeneous. Again, no assumption on K here. Okay, then the degree of the degree. So this is the degree of V of I. Okay. So this is thought of as a closed, the correct word is subscheme, but we will not since we haven't defined those things, I won't use it. At least it's a closed subset of Proj of S. okay, is the degree of this, that's it's a definition, is the multiplicity of R mod I, S mod I. Okay, so this is what we will call the degree of this thing, and here is a proposition. Okay, so the sort of geometric explanation behind degree. Okay. With notation as above, assume K is infinite. Okay. Let D be equal to the dimension of V of I. Okay. Then for general linear forms, so what does that mean? For general linear forms, okay, so what does this mean here? It means that just randomly pick something. Okay, as long as we allow the coefficients to be something arbitrary. So general linear forms L1 through LD. Okay. V of I intersect V of L1 through LD consists of degree VA points counted with multiplicity. I will explain what would be counting with multiplicity mean once we see the proof. Okay, proof. Okay, so if we if we go back to the proof of the how we sort of calculated this expression for the Hilbert series, which is some numerator Laurent series divided by 1 minus t to the some exponent. If we went back to the proof relied on going modulo non-zero divisors, and when there is no non-zero divisor, one of two things could be done. So we'll do the second one that we did, which was to saturate out the finite length submodule. Remove everything that is there, which is killed by a power of the maximal ideal. Okay, so then we will pick up a non-zero divisor, and then we go modulo that. So now we have brought down dimension and keeping the same multiplicity. Okay, so this is what we want. So so we'll do the same thing. Note that V of I is same thing as V of I colon M infinity, meaning we saturated out the component of M. Okay, so this is the observation that any homogeneous prime ideal which contains I. Remember, I is a smaller ideal than this, or not. I is subset of this thing. If a prime ideal contains this, and maximal ideal multiplies something to 0 in that thing, then the maximal ideal will multiply it into the prime ideal. But maximal ideal is not a subset of the prime ideal, so that something should be in the prime ideal. Okay, so therefore this. Okay, so the saturation is also V of I is equal to V of this. Okay, so repeat. So doing this, so replace I by I colon. So this colon is an S. A colon, saturate out M. Okay, so now S mod I has a non-zero divisor. So this was the argument that we did earlier. Okay, so now go modulo that thing. We have reduced dimension and now use induction, okay, on dimension. So yeah, so where is K non-zero as a non-zero divisor in degree 1? This is where K is since K is infinite. K has to be large K has to have so many elements so that it is not the degree one part is not contained inside the union of the associated primes. Okay, so this is K is infinite, and so with this we are able to so let's call this non-zero divisor L1. Okay, so now replace I by I plus L1, I plus I generated by L1. Okay, so now dimension has dropped. Okay, and we noted that E, so remember that the multiplicity of S mod I is ED plus 1 in the notation of S mod I. Okay, so this is from the notation from previous lectures. Notation from previous lectures. Okay, this is same thing as ED, the multiplicity of S mod I plus L1. Okay, and then we can just repeatedly do this and then get to that. Get to the situation where, so now repeat this. To reach the situation, dimension of S mod I equals 1. Okay. Again, we can factor out. So now if we write I as some J1 intersect J2, some Js, intersect Js, okay, and again without loss of generality, I could be maximal ideal need not be associated to this, okay, and so this is a irredundant primary decomposition, okay, and then and again without loss of generality, I equals the saturation of M. Okay, so none of this is associated, maximal ideal is not associated to that list. Okay, so then now it's just E1 of E0. It's one dimensional. R mod I is sum of E0 of R mod J I goes from 1 through S. Okay. Now each of these things, so radical of Ji is a prime ideal, homogeneous prime ideal. Okay. So let's say Pi such that Pi is not equal to M and there's nothing in between, and height of M mod Pi is 1. So this is maximal in that thing. So these are the close points of the spectrum of the Proj. Okay. And but this particular thing will have a multiplicity not equal to 1, and that is what we meant by saying counted with multiplicity. So these are S distinct points, but the point corresponds to the maximal, corresponds to the prime ideal Pi, but it has a multiplicity which is the multiplicity which is this number. Okay, so that's what we meant by saying the degree. So this is the degree, by the argument this was the degree of V of I. Degree of Vi is, after we reduce it, it is the number of points counted with multiplicity. Okay, so this is the this is how it's calculated. Okay, so we will stop at this lecture now. In the next lecture, we will look at degree in a slightly different way, and then we will do some Macaulay example which illustrates these points.